All right, factors affecting London dispersion forces. We talked about last time, let's go over the shape of the molecule. It's important, long, skinny ones, of course, have stronger dispersion forces because their clouds are more polarizable across the linear type fashion. Now, these long, skinny ones versus the shorter, fat ones, or the ones that have more branches to them, they don't pack as well, so some of their forces may be lessened due to that. So due to the increased surface area of the longer skinny one, like the N-pentane here, you can see its boiling point happens to be higher than neopentane, where they're more of a branching pattern there. Another thing to consider when looking at and comparing different data sets, because this is what they do for IMFs. They give you data sets, like they'll give you this table of boiling points and expect you to be able to explain the differences in their properties, their IMF forces, based on the boiling point data. So the presence of a pi bond. Pi bonding. If you remember, pi bonding are the additional bonds in a double or triple. So remember, a double has 1 sigma and 1 pi. A triple bond has 1 sigma and 2 pi bonds. So here I used organic examples because they love to use organic examples on the AP exam. So in a way, we're sort of reviewing a little bit of organic chemistry in this process. If you remember alkanes, alkenes, alkynes, these are all hydrocarbons. And alkanes, alkenes, alkynes, all hydrocarbons, of course, are going to be in that realm of being nonpolar because they don't have polar bonds. Their electronegativity differences between the carbon and hydrogen are not big enough for that. So here we're going to now compare them with reference to presence of single bonds, double bonds, or triple bonds. So the alkanes, the A and E ones, have only single bonds. The enes, they have a double at least, and the ines have a triple in them. Okay, just recalling those things about organic chemistry. And looking here, these are the C2 ones. So if you remember the prefixes, they're for naming organic. Meth is for 1 carbon, eth is for 2 carbons, prop 3 carbons, bute is 4 carbons. Then it goes into the regular prefixes that you know, like penta is for 5, hexa is for 6, hepta is for 7, octa is for 8, and so forth. Nona is 9, and 10 is deca. So remember that naming system so that you have a good idea and are familiar with it. Now, if you're looking here at these particular molecular structures and then comparing their boiling points, this is where we really need to look at. So let's compare the anes to the enes, the single bonds to the double bonds, and look at the pi bonding here and how it affects it. While part of it is the shape. So these guys right here are going to be tetrahedrals. 2 tetrahedrals put together, because you have the 1 carbon with the 3 hydrogens bonded to the 1 carbon with the 3 hydrogens. So those are going to be tetrahedrals. If the ethene has a double bond between them, now they're going to be like 2 flat triangles, 2 planar shapes together. And then if you're looking at the ines, the triple bond makes it like completely linear, okay? Straight linear chain there. How does that affect the boiling over here? Well, obviously the ethane's boiling point happens to be higher than ethene's. Now they have the same number of carbons and hydrogens, so their molecular weight's the same, their number of electrons would be similar, and well, they wouldn't be exactly the same, but they'd be close. It's about the polarizability of the cloud, and that's going to be mainly based off of the shapes here. The tetrahedrals more look like the long, skinny type thing, whereas these planar ones branch out a little bit. And the branching out is what's going to affect, not in this particular case, the double bonds are not stronger, because if you look at the boiling point, it's lower. So that means its forces, double bonds are stronger than single bonds within the molecule. Those intra forces are stronger. But between the molecules, due to the way that it branches out and forms this planar shape, okay, the planar shape's not allowing for the polarizability of the cloud to be the same as the ones with the tetrahedrals. So the ethane cloud obviously is more polarizable based off of its shape in order to get this lower boiling point in comparison to ethene, which has, I mean, the ethane boiling point is higher than the ethene boiling point because its cloud is more polarizable. So the London dispersion forces in ethane are stronger than in ethene. And it has to do with the shapes because they're very similar in size, so that can't be the factor. Now, the linear one, the triple bond one, okay, it has the highest of the three. And why is that? Because that linear makes it really like skinny, makes that cloud more polarizable. So once again, going back to when we're talking about factors, yes, we're looking at the size so that we know the number of electrons, so we know the polarizability of the cloud based off of larger clouds are more polarizable. But shapes also affect this polarizability of the cloud. So the linear shapes make it nice and skinny, makes it more polarizable. The planar shapes branches it out a little bit, not as easy to polarize or is not as strong in terms of its polarizability. The tetrahedrals are three-dimensional at least, so that gives a good space for the cloud to polarize on either side, as opposed to the flat shapes here. You see the trend is the same in the three carbons, the propane, propene, propyne. The one that has the triple bond in it is the most linear, which is the most polarizable, which has the highest boiling point. Then comes the ane with the tetrahedrals. And then this one has they have tetrahedrals on the end, but this is the linear part. And this would be the planar part of the molecule. And the enes, the alkenes, are always going to be the ones with the lowest out of the three. Same trend happens with the four carbons, the butane, butene, butyne. Butyne being the strongest with the highest boiling point. And also the pentane, pentene, pentyne. You can see here the triple bond, and it has the highest boiling point out of the three. So the pi bonding does affect it because it affects the shape, which is going to affect the polarizability. And here within the groups, the alkenes are going to have the lowest, then the alkanes, ANE, alkanes, and then the alkynes are going to be the strongest. Due to this, see this nice linear shape, this nice skinny linear molecule, more polarizable. These are the flat triangles I was talking about. Here's one of the triangles. Here's the other triangle, the T-planar ones. Branches it out, it's not as polarizable. And then of course these are the tetrahedral ones that are three-dimensional, which allows for a little bit more polarizability than the flat arrangement. So you could be presented data tables like this, and you'd have to be able to explain the differences between the strength of the forces based off of their boiling points. Going into now the next category, dipole-dipole interactions, dipole-dipole forces. These all are from ones that have permanent dipoles. So these guys are all polar substances. In order to have a permanent dipole, it has to have a dipole moment that goes one direction. You have to have the partial negative, partial positive charges that are permanent on the molecule. This example, HCl, of course, hydrogen chloride. As you can see, the dotted line here is representing the IMF. This is the dipole-dipole force. I like to go dip-dip for short. This bond right here is the intraforce. This is the polar covalent bond. This is the polar covalent bond. So this is a full intraforce here. Now what you see here, of course, the permanent dipoles, you have a partial positive side, a partial negative side. So the partial positive side of one molecule attracts the partial negative side of the other. And that's basically what we're seeing here for dipole-dipole interactions. Now this is an interesting diagram. Like I said, positive end attracts the negative end of another molecule. So they're between here. Forces are important, when they are close together. So we're really kind of comparing the solid phase here versus the liquid phase in these particular examples. Now we know in the solid phase, and this one's showing you, this is the acetylnitrile molecule. So let me draw it for you. No, there's another C in here. Sorry, hold on. Nope, that's not where the double bond goes. One more C. We go C and then N. All right, so as you can see here, the dipole moment goes towards the N. That's what's showing you here. The blue is the nitrogen, the white is the hydrogen, and then the black is representing carbon. So nice polar, and then it has this linear side of the molecule, which more polarizable. In the solid, though, you see all of these dotted lines that are red between. Those are the IMFs. These are the dipole-dipole forces holding it together. And what you're going to see here is these are all attractive for the solid phase. Everything's attractive in here because they're in a fixed position. They're just vibrating in place. Fixed position, vibrating in place. Everything is attracted, and it's arranged in sort of like a crystalline fashion. Okay, a repeating pattern type fashion. If you look at the liquid phase, though, where some of the attractive forces have been loosened due to addition of heat that helps loosen them a little bit, and these molecules have more kinetic energy, so they're moving, they can flip and turn and move. They're spaced out just a little bit more than the solid, not a whole lot, but a little bit more because they're flipping and moving. If they're flipping and moving, then you also get these repulsive forces in there, because when they flip and move, sometimes the nitrogen ends end up colliding. So you have the negatives repelling the other negative sides. And that's what makes, you know, the liquid pattern a little bit different here. It has the attractive forces, which are in red, but it also has some repulsive ones because the molecules are moving more, they have more kinetic energy, they're flipping and rotating. So you do have some repulsive forces as well as the attractive forces, and that's why, you know, you have more kinetic energy, these particles are moving more. The forces are still there and they're still kind of compact and close together, but as opposed to, say, like gas where they're just randomly going everywhere. You do have repulsive and attractive forces, as you can see here in the liquid phase versus the solid phase, which would just be attractive forces holding them in fixed position. Now, another way that they can give you comparisons here for data. As you can see, each of these molecules have different data listed below. Propane, hydrocarbon, so this one's non-polar, we know that off the top of our head. This one has an oxygen in here, so it's definitely going to have dipole moments towards the oxygen. Same thing here, dipole moment's going to go towards this oxygen, so there's partial negative sides, okay? These are partial positives, and so forth. So we definitely see, now these guys have polarity. This one goes this way, of course, partial negative, you know, partial positive, and so forth. What they're comparing here, though, if you're looking at the dipole-dipole ones, the molecular weights are similar, okay? Molecular weights are similar, so the London dispersion forces aren't really different for these molecules. What's different about them is the polarity of them. How polar are they? The ones that are more polar are going to have the higher boiling points. And how do we tell that based off of this data? The weights are about the same, so it's not the London dispersion forces that are, you know, the polarizability of the cloud is affecting it. You look at the dipole moments, which is this little mu here, dipole moments, 0.1 versus 1.3 versus 2.7 versus 3.9. Looking at the data and honing in on the data. The one with the highest dipole moment, as you can see here, has the highest boiling point. The next one, 2.7, its boiling point is less. And then, of course, with a lower dipole moment, its boiling point is less. So how polar the molecule is definitely matters. And part of its dipole moment and strength of its dipole moment has to do with its shape as well, and the direction, and whether it's more linear, long and skinny versus fat and you know, branched off together will play a role into that dipole moment, degree of the dipole moment. So for this particular one too, looking at the shape and the relative orientation with this same data, because we were looking at those four, but this one also has the methyl chloride example in here, which would be this particular one. I put the ball and stick models in here for you to kind of really get the idea of the orientation and the shape of what's going on here. So here's our propane, 3 tetrahedrals together, nonpolar, very just London dispersion forces. So the boiling point would be the lowest. But if you're looking at dimethyl ether, where you have the dipole moments going towards the oxygen, but it's more centralized in the middle rather than on the ends, the polarizability of the cloud, is going to be slightly different. So it's not as polar. Whereas the methyl chloride, it goes directly towards the chlorine. You definitely have an end there. And you can see as you get more, here's your dipole moment going towards the oxygen here and going towards the nitrogen here. This one's definitely longer and skinnier, and that's going to be the acetylnitrile, this one with the highest boiling point, because its dipole moment is higher and more directional in that particular case. So you could get a data table like this, and then you would have to explain, well, the acetylnitrile has the strongest forces because the boiling point is higher. Also, the dipole moment is larger. So I know it's more polar, and more polar creates a higher partial charge, which is going to increase the strength of the force. So a more polar, a larger dipole moment increases the partial charge. The partial charge then is going to increase the force of attraction if it's higher. This one also compares 2 different categories, things that are polar with things that are non-polar. So if you're looking at things that are comparable in size and shape, the dominating force is going to be the dipole-dipole interactions. If they're similar in size and shape, that's what we look at. If one is much larger than the other, then we would really want to look at dispersion forces to compare. Okay, so looking here, we have these are our alkanes. We know these ones are all nonpolar. Then we have polar molecules like water, methanol, ethanol, and propanol. And if you don't remember organic chemistry, remember the alcohols have that OH group on the end. And that OH group on the end is going to cause the molecule to be asymmetrical and polar. So all of those are polar. Now they also have OH bonds, which is going to contribute to hydrogen bonding, which we're going to talk about in a minute. So they not only have London dispersion forces, they also have dipole-dipole forces and hydrogen bonding. But if you compare the ones that are of comparable size, like methane and water, which one has the higher boiling point? It's going to be the one with the dipole-dipole interactions. All right. Whereas, ones that are a little bit larger, super large molecules will compare where they have lots of massive amounts of electrons and a more polarizable cloud may actually have stronger forces than something that's really small with hydrogen bonds. One other concept AP wants you to know is looking at dipole-induced interaction. So this is like the interaction between a polar molecule and a nonpolar molecule. The polar molecule is going to induce the dipole in a nonpolar molecule in similar fashion and creating that like it would if it was regular London dispersion forces. But these forces are always attractive. You can see oxygen here, which is nonpolar, and then water, of course, which is polar. So the water is going to induce the dipole into the oxygen. The cloud's going to shift over, and you get the partial negative on one side, the partial positive on the other, and now you have an attractive force between them. Okay, attractive force between these. This is the polar molecule inducing the dipole in the nonpolar molecule. Here is also showing you in a different graphic the same thing. This is going to be the polar side or the partial negative side of the water. It induces the dipole, pushes the electrons to that side of the oxygen and creates an attractive force between them and IMF. Okay, so the strength of these forces increases with the magnitude of the dipole. So the more polar the molecule, the larger the force, and the more polarizability of the nonpolar molecule. So if the nonpolar molecule has more electrons, can be more polarizable, you can increase the strength of the interaction. And now we're going to do an example just like this and think about how it's going to work. Which has stronger attractive forces? The water and the carbon tetrachloride or the water and the carbon dioxide? Now, in this particular free response example, you would need to discuss both of the IMFs involved when you're talking about it in your answer. So I'm going to give you a couple of minutes to go ahead and think about that. Which one is correct? Which one has the stronger attractive force? The water and the carbon tetrachloride, or the water and the carbon dioxide? Anybody have an idea which one would be stronger? The water and the carbon tetrachloride, or the water and the carbon dioxide? Okay, let's think about these things. The water is the same for both choices, so we really don't need to focus on the water. Oops. What we really need to focus on is our carbon tetrachloride and our carbon dioxide, because those are the differences here. What's different about them? What type of molecules are they? Are they polar or nonpolar? And if you don't know, you can draw them out. You know, that's something that you could do. CCl4, draw it out. All right, you know, end up getting your Lewis dot structure. Okay, and we get this tetrahedral shape, very symmetrical. It's nonpolar, good. No dipole moments. The dipole moments all cancel out in that case. We're drawing carbon dioxide, right? Looking at carbon dioxide, also nonpolar. Dipole moments cancel out. They're both nonpolar. Now, looking at them, though, what's going to affect the attractive forces? They both only have London dispersion forces. What's the next feature we need to look at between the two? If they're both nonpolar, the size and shape, exactly right. One's tetrahedral, one's linear, but let's look at the size too. Chlorine has 17 electrons per chlorine atom. The carbon only has 6. Oxygen, so if we're looking at electrons, so the polarizability of the cloud, 8 electrons here, 6 electrons here, 8 electrons here, 17 each for each chlorine. Okay, number of electrons, this one has 6, and then this is 17. Which one has massively more electrons? Yes, the carbon tetrachloride has more electrons. So yes, the shape is definitely a factor to look at too, but here there's a huge discrepancy in the number of electrons. The carbon tetrachloride's cloud is going to be a lot more polarizable because it has a lot more electrons in it. In that particular case, since there's such a huge difference in the number of electrons, I would focus more on the size in this particular case. So I would declare then that the water and the carbon tetrachloride happens to be the stronger force because the London dispersion forces that will be created in the induced dipole of the carbon tetrachloride is going to be much stronger than the induced dipole forces of the carbon dioxide due to the massive size of the cloud. Now, how do we explain this? Because we need to talk about IMFs in our answer here for both substances here. Water is polar with LDFs and dipole-dipole interactions. We know this. It also has hydrogen bonding as its predominant IMF. So out of the 3, water has all 3. We haven't really gone into hydrogen bonding yet, but we will in just a minute. You've heard of it before, so it's just basically a very hyper dipole-dipole type interaction. It's much stronger than that because the electronegativity difference is higher, but it is the predominant IMF, so hydrogen bonding is going to occur in the water. Both the carbon tetrachloride and carbon dioxide are nonpolar and have LDFs, London dispersion forces. But due to the fact that however, the carbon tetrachloride has a larger electron cloud, than the smaller carbon dioxide. So it's more polarizable, and I can't underline this enough. This is a specialized term that needs to be in the answer, more polarizable. Therefore, there's a stronger attractive force between the water and the carbon tetrachloride. So when you're looking at this, these are the kind of things that you want to state in your, making my claim here that the stronger forces between water and carbon tetrachloride, and then my reasoning explaining both types of IMFs in the answer as you're going along. And this is a very typical free response type question they would ask you to explain with regards to IMFs. Now we're going to look at the differences here in this particular graph, because this is another way they could give you data, looking at these trend lines. If you're looking at this particular graph, you have boiling points in Kelvin versus molecular weight, and it's showing you the different groups. So like here's the halogens, here's the oxygen group, here's the nitrogen group, and here's the carbon group, and their trend lines. What you notice about the carbon group, it just goes up in a nice linear fashion. We know methane happens to be nonpolar, so it's going to have a very low boiling point. That's expected, that increasing boiling point following that trend. Great. The polar series follows the trend until you get to the smallest molecules. So we have, here, like the water, the oxygen group, this would be like H2S, and this would be like H2SE, following the elements in the group as you go down the group. Here, HF, this would be HCl, and then HBr, and so forth, HI. What you're seeing here is these guys don't follow the trend. Water, hydrogen fluoride, or ammonia. They do not follow the trend at all. They are wacky higher boiling points in comparison to the rest of their group. Now we need to talk about why that is. That is because of hydrogen bonding. The specialized dipole-dipole interaction that's unusually strong. And it only takes place between these four elements. H-fon, I say having fun with H, H-fon, okay? H with F, H with O, or H with N. Only particular ones that can do hydrogen bonding. And it shows you here it has to have the interaction of the H to the O, or the H to the F, or the H to the N within the molecules themselves. Now, why is this? Why does it create this bigger dipole interaction, this unusually strong dipole interaction? Well, it's in part arises from the electronegativities of the oxygen, hydrogen, and fluorine. The nitrogen, oxygen, and fluorine. Those ones have higher electronegativity values, so the electronegativity differences will be higher. The other thing, though, that makes it a dramatic increase in strength is due to the fact that hydrogen's so small, and it's so small it only has that one electron, one proton arrangement. Being so small, though, and if that electron spends more time around the electronegative element like oxygen or fluorine, it exposes the hydrogen nucleus, which has just the one proton. But exposing the one proton leads to a higher positive partial charge on that side. And if you have higher partial charges or stronger partial charges here, you're going to have stronger interactions, stronger forces. So due to the fact that it exposes that proton on the hydrogen, you get a higher partial positive charge, and then therefore leads to the stronger attractive force of hydrogen bonding. In this example picture I like because it's showing you ice, but it also shows you like the arrangement of the ice here, where you have 6 water molecules that form this ring. But you can see there's a lot of space inside the ring here. And that's why, water is less dense as a solid than it is as a liquid, because you have this, it actually spreads out and forms this 6 water ring arrangement. And here, just showing you the dotted line again, which is the hydrogen bond versus the covalent bond, and you can see their distances 1.8 angstroms versus 1.0 angstroms, looking at the arrangement here of that hydrogen bond. Going back to shape though, going back to that a little bit here, IMFs and orientation and shape here. Because water versus ethanol. Water, of course, we know, our little Mickey Mouse ear example over here. Ethanol, though, if you don't remember ethanol, it's one of those alcohols that has this OH group on the end. But ethanol is 2 carbons because of the eth part here. So the 2 carbons on the chain. So this part of the side of the molecule is kind of nonpolar. Over here to the right with the OH part is the more polar side, and it will form these hydrogen bonds. So you kind of have 2 things going on here. Water is smaller. It's can establish more bonds between the molecules because it's smaller and it can arrange itself this way. And it has polar ends on different sides of it, whereas ethanol only has the one polar end. Like over here, you have no partial charge end going on. So water forms more hydrogen bonds than ethanol based on its structure. But ethanol is more massive in terms of like electron cloud. So technically, ethanol should have larger London dispersion forces than water. Ultimately, though, if you look at the data and compare boiling points or you compare vapor pressures or anything like that, you would see that water's hydrogen bonding and its ability to form more hydrogen bonds makes it a little bit stronger in terms of the actual property data. Vapor pressure, which we're going to go into detail, lower vapor pressures means stronger forces. The molecules don't escape the liquid as easily because of the stronger forces. They're slightly different, 0.08 versus 0.03, but the data does show that water has a lower vapor pressure, so therefore water has the stronger forces in comparison to ethanol. Now you could also compare the boiling points, because I think ethanol is somewhere in the 70s, like 78, and water is 100, the normal boiling points would be. So obviously the boiling point data does point the same direction where water has stronger forces than ethanol. They both possess hydrogen bonding though, and the dipole-dipole and the London dispersion forces. It's just the way it's shaped, and the way that it can connect and form the different forces does affect these properties. Ion-dipole interactions. Now we're going to go into this a lot more detail when we get to solutions, but this is also an attractive intermolecular force between different things. It's between ions and obviously polar molecules that have dipole interactions. It's an important thing that we see in solutions. The strength of these forces is what makes it possible for ionic substances to dissolve in polar solvents. Now, ionic substances, of course, form these full charges, the anion, the negative, or the cation with the full positive. Now, what you see here in this model of the molecules is the water surrounds each one, but it surrounds it in a different orientation or manner. The hydrogen sides point in, because that's the partial positive side, towards the chloride, because the chloride is negative, anion. On the sodium side of things, where it's a positive cation, the oxygen sides point inward, so the partial negatives point in towards the positive. And they surround them, and they form these dotted lines, which are these ion dipole forces. The water's polarity and these partial charges helps to pull the salt particles apart. So we're taking the sodium and chloride and pulling them apart, and then the water completely surrounds each individual particle. That is true of all soluble salts. The ones that are soluble, the water has enough strength to pull them apart and surround them. When we're talking about salts that are insoluble, like ones that do not break apart in those solubility rules, something like AgCl would be an insoluble salt. That is because the strength between the silver and the chloride, that particular bond, that ionic bond, that Coulombic attraction is stronger than the water, so the water doesn't have the ability to pull it apart. And that's why it would just fall to the bottom and stay a precipitate, stay a crystalline solid. We'll get more into this in a couple of topics ahead when we get to solutions, but I wanted to introduce it here since it is an attractive force between 2 separate chemical species. They tend to be stronger too in general over just regular dipole-dipole forces, just to note that. And here's a nice little diagram, and you can find videos on this too where it shows how the water molecules pulling apart the salt crystals and surrounding them. And then we say it's hydrating them. It's giving, surrounding them by water is hydrating them. So that's another thing to definitely look at here when we're talking about ion-dipole interactions. Now, summarizing all the forces here in our nice chart. So this is a good way to refer to them and figuring out which type of force that they have by looking at this chemical species. Are there ions present? Well, if there are ions present, okay, are there polar molecules present as well? If so, then we're talking ion-dipole forces here. If no, then you're just talking about regular ionic bonds, the Coulombic attractions, the lattice energies. And this, of course, way stronger, much more stronger than anything else on this table. It's in the intra realm. This goes under the intra side of things. So it's going to be much higher and much stronger in terms than anything over here on the other side of the chart. Now, if there are no ions present, now we're talking about polar, nonpolar, covalent only molecules, period. If there are polar molecules present, then we look for HF, HO, or HN. If they don't have HF, HO, or HN, that's just going to be right here, regular dipole-dipole forces. If it does have HF, HO, or HN, then it falls under the hydrogen bonding category. If there are no polar molecules, this is going to be nonpolar only. That's going to have only dispersion forces, completely only dispersion forces. Now, this is the generalized increasing interaction strength. This really only works if we're talking about comparable sizes here. Once we get into non-comparable sizes, then you have to go based off of the data. So speaking of our regular general trend of forces by strength here, we have LDF is the weakest, then comes dipole-dipole, then comes hydrogen bonding. These guys are all falling under that IMF category here. And then ionic is the greatest, and it's under the intra particular side of things. So I want you to take a moment, which has stronger forces, and try to think about this. Iodine or water? Take a moment to think about that, and we'll come back in just a second. Okay, any decisions? Who wants to make a claim? Which one is stronger? Which one has stronger forces? What do I know about these two things? What do you know about iodine? What do you know about water? What do you know about iodine? Iodine is nonpolar, definitely, you know that, good. It is got no dipole moments. It's completely nonpolar covalent, good. We know that water's polar, good. What else do we know? Anything else about their properties? What do we know about their states of matter? At normal conditions, I'm sitting here in this room, what would H2O look like? What phase would it be in? It would be a liquid, exactly right. How about iodine? I'm sitting here in this room. How would the iodine exist? Is it a gas? Is it a solid? It's a solid, right? Because we talked about that earlier in this PowerPoint, that the halogens are an interesting group because fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid at room temperature, right? You remember talking about that at the beginning? Now coming back to you. What does that tell you about these phases of matter? If iodine is a solid at normal conditions, and water is a liquid at normal conditions. What does that tell you about the strength of their forces? If you felt like there was a trick to this one, well, there is. Definitely. The solid is stronger. Definitely. Exactly right. In order to be a solid, you would have to have stronger forces because it's holding the particles in those particular fixed positions. But we know that iodine, you said, was nonpolar, and we know that's going to only have LDF forces. The water, of course, is polar, and it has the H bonding, right? So if we're looking at that and we're trying to do it based off of this general ranking, well, that's not going to work. We have to know the properties and use the data in order to explain which one has stronger forces. So in this particular case, we would say iodine has the stronger forces because it's a solid at room temperature. That means, of course, the forces have to hold the particles in fixed position, whereas the liquid particles can flip and turn and rotate and have more kinetic energy. So in this particular case, the size of those LDFs, iodine has 106 electrons in its cloud. It has 2 atoms of iodine. They both have 53 electrons. It's a linear shape. It has got a very polarizable cloud, and therefore its London dispersion forces are much greater than the small hydrogen bonding forces in the water. Now that's the predominant one in the water. The water also has London dispersion dipole-dipole interactions. However, because it's so small, those London dispersion forces, basically being as massive as they are going to affect the comparison of strength here. So the LDF are stronger, and we know this because it's a solid. It's holding those particles in those fixed position. Now let's talk about some of the other properties and data they could give you that you would need to be able to compare. Viscosity, surface tension, boiling point, melting point, and vapor pressure. Mainly the ones that they do give you data on are going to be these 3. You might see viscosity, you might see surface tension. I rarely ever see those, but you never know. These 4, though, as they get larger, the forces are greater. Okay, so as those 4 get larger now, vapor pressure lower, that is when the forces are greater for vapor pressure. What is viscosity? Viscosity is the resistance of the liquid to flow. So like molasses has very high viscosity. It's very thick, whereas water, it pretty much just pours. So the viscosity of water would be a lot lower than molasses, or even syrup for that matter. So as the viscosity increases with stronger forces and it decreases with higher temperatures, obviously, because if it has higher temperatures, it's giving it more kinetic energy and moving, the particles would move faster and slide faster. But they could give you a data table like this where they give you viscosities to examine. And obviously decane down here has the largest viscosity. All of these are hydrocarbons, organic substances here, right? The 6 carbons through the 10 carbons. What you see here, though, of course, the decane is more massive, it's going to have more electrons, more polarizable cloud. So that would explain why its viscosity is much higher in comparison on the data table. Surface tension, not really sure they're going to ask about this, but good idea to know what it is. The water strider sitting on top of the water there. The surface tension is that, inward force, of course, that gives that little, tension on the top of the water there in that particular example. And of course, it would increase with stronger forces. Now let's look at phase changes and talk about changing phases and boiling points and melting points, because that kind of all falls under the same realm. We're going to talk about the actual heat amounts and things like that when we get to Unit 5 and the heat that it takes to change phase for certain things. Remembering the endothermic processes where you add energy, that would be melting, vaporizing, subliming, Exothermic, where you would be releasing energy, would be condensing, depositing, or freezing, okay? This is a way, though, that they can give you data that you would need to know that correlates to boiling points and melting points. They give you heat of fusion values, and the heat of fusion values would be in kilojoules per mole. They give you different values of heat of fusion. They're referring to basically how much energy do you need to add to make it melt. So it gets that to that melting point required to melt it. So comparing those butane, diethyl ether, water, and mercury, of course here the heat of fusion amounts, you would compare them. Mercury's the highest, but mercury's kind of in a different category too because it's in that metallic bonding category. So this would have intra forces because it falls under the metallic bonding category. So it would be looking here and referring to that in order to establish a pattern. So in this particular case, out of these three, it's very close, but the diethyl ether actually, the melting point would be the highest for diethyl ether. We're looking at heat of vaporization though, which is the amount of heat needed to boil it to go from the liquid to the gas phase. You compare these, which would be the middle column. Water, of course, is the highest out of the ones that have IMFs because these are the only covalent ones. Mercury's in the metallic bonding category. But as you can see, the water, therefore, would have the higher boiling point and the stronger forces in that particular case. Also, heat of sublimation is going directly from solid to gas. So as you see a heat of sublimation being higher, once again, that would be for water here. If we're just comparing the covalent compounds, that one would have the strongest forces based off of this particular set of data. Now, if you were looking at all of them on here, then you would declare mercury, of course, the highest, but it has the metallic bonding, those intra forces as well. That's going to, this is going to be higher than any intermolecular force available. Another thing we're going to look at when we get to the heats is these heating curves, okay? Probably saw them last year briefly in the spring. The heating curves, like the solid is heating, then it melts, then it's heated, kinetic energy is increasing, then it completely vaporizes, and then it's over here as a gas. One thing you should notice about them is that the melting points and boiling points goes into pulling apart the molecules or spacing them out more, getting them a little bit more kinetic energy. So the kinetic energy increases as you're heating it. Then you finally get to a point where it can overcome the forces, okay? And loosen the forces when it melts it, so then it can flip and rotate and turn. And then when it finally gets up here to the vaporizing stage, that plateau is a lot wider, and it's a lot wider because it overcomes all of the forces, because technically a gas, if we're following the kinetic molecular theory, one of the assumptions is that gas particles do not have any attractive or repulsive forces. So overcoming all those forces takes a lot of energy, and that's why that plateau is going to be a lot higher. The temperature, of course, of the substance does not rise during a phase change. It's using the energy to break apart the particles, pull apart those molecules, and space them out. So that's why we have plateaus versus we have slopes here on our heating curve. We're going to go into more detail with the heating curves, like I said, later, but this is part of the deal with the phase changing. And spacing them out, it has to do with those intermolecular forces. Vapor pressure, liquid and vapor reach a dynamic state of equilibrium when you're in a closed container. So you have to be in a closed container, because if you're not in a closed container, then it's just going to go into the atmosphere and evaporate. But if you're in a closed container, it will eventually get to a same rate deal where it's condensing and it's evaporating at the same rate. Now the thing about vapor pressure though is if it has stronger forces, less of it's going to be able to escape and evaporate. So you'll have less vapor pressure sitting on top of the liquid in the closed container. If it has a lower vapor pressure, it has stronger forces. If it has a higher vapor pressure, it's going to have weaker forces. Just really depends on the substance that's located inside the closed container. So as more of the liquid particles escape and become gases, what's going to happen is the pressure, of course, is going to increase. What's pressure again? It's when the particles are hitting the walls of the container. So that would be in the gaseous phase. Now we'll get more into pressure in the next lesson when we're starting to talk about gas laws, but note that as you have a higher vapor pressure, obviously the pressure part being higher, it's causing more collisions with the walls of the container. One other thing to look at too, at any temperature, some of the molecules will have enough energy to break free, because each, there's always a certain part of particles, like the majority of them are here in the middle, but there are some that have more kinetic energy, some that have less kinetic energy. So this little blue area is the amount that can escape at any particular, lower temperature. If you raise the temperature, though, then you increase the fraction of molecules that can escape. They have enough kinetic energy now to escape the liquid phase. And so the thing shifts over here. And that's what happens as you continue to add heat and you've reached that boiling point. Now you're giving it more energy, so more of the molecules end up being able to escape. And if you were to do it in a not closed container, like put a pot of water on a stove and just you turn on the heat and you let it boil, eventually over time, all of it would escape, because all of it would eventually have enough kinetic energy to escape. Let's talk about the definition of a boiling point. Boiling point, of course, is defined as the temperature at which the vapor pressure equals the atmospheric pressure. So that's when it can escape, when it finally gets to that point. And obviously things with higher boiling points have stronger forces because it takes more energy to reach that particular equal state of the vapor pressure equaling the atmospheric pressure. Boiling points and melting points, especially the boiling points, are affected by pressure and temperature. So when I say that water boils at 100 degrees Celsius over here, it actually boils at many different temperatures depending upon the pressure that it's at. This is a vapor pressure curve, by the way. You probably saw them last spring. But when I'm referring to water boiling at 100 degrees Celsius, I'm referring to the normal boiling point. Normal boiling point is at normal conditions, which would be about room temperature and standard pressure. Standard pressure happens to be 1 atmosphere, 760 torr or millimeters of mercury, or 101.3 kPa, kilopascals. So keep that in mind when we say, hey, it boils at this. We're really referring to the normal one, which would be at standard pressure. Okay. Now, example here, looking at and comparing different vapor pressures. I have this nice flow chart here to help you figure this out, and this other word, volatility. Hopefully you won't know that volatility being high means it's escaping very quickly. Volatility is low, that means not as much as escaping as easily. So I like to think about this in terms of like the gasoline example. Gasoline, there we go, versus water. And I'm sure some of you have pumped gasoline at a gas station before, and maybe you haven't, but if you have, you probably have noticed any once in a while when a few drips come out. Of course, I've gotten on my jeans before, and then I'm like, oh darn it, what's going to happen there? Oh well, 2 seconds later, it's gone. The little dot that was on my jeans is no longer there. Why is it no longer there? Because gasoline is nonpolar, it's octane. It evaporates very quickly. It's very volatile. The vapor pressure is super high, so the boiling point's really low. Whereas water, on the other side of the coin here, the volatility is low. The vapor pressure then is low. The boiling point is high. So before we even answer this question, which liquid has the stronger IMFs? First, let's look at our two closed containers here. Which container has the higher vapor pressure? Is it container A or container B? With liquid A or liquid B? Yes, you see all these particles in here, much more in the gaseous phase. B has got a higher vapor pressure. That means this has a lower boiling point though. So now that I've looked at and evaluated this particular, scenario here, which liquid has the stronger IMFs? A, very good. Yes. The liquid that has the stronger IMFs is going to have the lower vapor pressure because it's not allowing it to escape as much. Therefore, it's holding on to it, not allowing as many particles to escape. Liquid A has the lower vapor pressure. The particles are more attracted to itself, and therefore it doesn't escape as much, as you see in liquid B, which has the higher vapor pressure. So definitely stronger forces go with lower vapor pressure. Higher boiling points, lower vapor pressure. Couple more data-driven type questions, just two more, and then we're done with this. So, comparing the data given, determine the stronger IMF. Which has stronger forces, HF or carbon tetrachloride? Explain based on the data given. So here they're giving us dipole moments, they're giving us polarizability, and they're giving us boiling points. That's the data that they've selected that we get to evaluate. So here I would go over here and look at my HF, hone in on the data. Down here on my carbon tetrachloride, I'd hone in on the data. What say you? Which one has stronger forces based off of our data here? Which one has the higher boiling point? The higher boiling point is carbon tetrachloride. Yes, definitely. If you look at these other data points, the dipole moment, obviously we know carbon tetrachloride is nonpolar, so it's not going to have any measurable dipole moments. They cancel out. But if you check out the polarizability as well, look at those differences. The polarizability of HF, even though it's got hydrogen bonding and all that stuff, it's not nearly as polarizable as carbon tetrachloride. Why is carbon tetrachloride so much more polarizable? What's the huge difference here? We know it's nonpolar, we know it only has London dispersion forces, but what makes it so much more polarizable? The number of electrons, it's so much more massive. So therefore, its boiling point is much higher. So the extreme polarizability of the cloud makes those London dispersion forces a lot stronger than even the hydrogen bonding that's going on in the HF, which is a little bit smaller of a lot smaller of a molecule. All right, so the carbon tetrachloride has the stronger forces, it's higher boiling point, those LDF. You could also refer to the polarizability comparison. More electrons here, more polarizable, huge number there, definitely indicates the stronger force. Last example here is looking at this vapor pressure curve. Explain why N-octane has a lower vapor pressure and a higher normal boiling point than ethanol or water. So go ahead and compare that. Okay, N-octane has a lower vapor pressure and a higher normal boiling point. So if we're comparing here, looking at the normal boiling points, that's where they would be on the graph. We know the vapor pressure is lower at the different temperatures in comparison to based off of the vapor pressure curve. So octane versus water versus ethanol. Now octane, of course, what type of molecule is octane going to have to be? It's one of those alkanes, one of those hydrocarbons. What do we know about those kind of molecules in terms of their polarity? Are they polar or nonpolar? Is N-octane polar or nonpolar? Yes, it's nonpolar. Hydrocarbons always nonpolar because the bonds between them do not have a large enough electronegativity difference. Nonpolar, so this is going to have LDFs only, compared to water and ethanol that have H bonding, both. Okay. But explain why it has a lower vapor pressure, higher boiling point. What would you say about the forces? The forces of N-octane must be what? Off of this data, it must be greater. N-octane is nonpolar and only possesses LDFs. It's a long straight chain, much larger electron cloud than water or ethanol. The electron cloud is more polarizable, making it have stronger LDF forces, and that's going to show why the boiling point, the normal boiling point, and the vapor pressure being lower is greater for an octane having stronger forces. So keep that in mind here, this more polarizable, this idea that the London dispersion forces within those nonpolar molecules, if they are significantly larger, are always going to have greater boiling points, they're going to have greater forces, and you compare the data and reason it through the data. So if one has a higher boiling point than the other, the higher boiling point has the stronger forces, and then just work through it. If it's only LDFs, it's because it's got more size to it, more polarizable cloud, and that increases the forces of those LDFs to be greater than the hydrogen bonds in water or ethanol.